So to find K values, you ordinarily need to just look on tables, as I said, and be very careful to look up the very specific situation that you're in terms of what Reynolds numbers you're in, what kind of situation you have in terms of pipe diameters, etc. But there are a few things where there are formulas you can use to find those loss coefficients. One of the ones that you can use a formula for is this sudden expansion. So this is a small pipe sort of going right into a larger pipe suddenly. And in that case, there's a formula here. The loss coefficient is 1 minus little d squared over big D squared, all of that squared. When using this loss coefficient, you have to use the U value for the smaller diameter pipe. So you have to use that faster velocity when you multiply that loss coefficient by U squared in the preceding formula from the last lecture. For sudden contraction, similarly, there's a formula. Sudden contraction is 0.42 times 1 minus d little d squared over big D squared. So that's the opposite situation where you have a bigger pipe and it suddenly goes into a smaller pipe with a sharp contraction like that. So you have the small d here, of course, and the bigger D over here. So it's just the opposite of sudden expansion. So sudden contraction has a formula you can use as well. Exits of all types, a pipe just going into some larger pool of fluid. Whether it's a sharp exit like this or a smooth exit doesn't seem to matter. K is equal to 1 for those exits, so that's an easy one to get. And then finally, sharp-walled entrances, the last of the ones that's sort of worth thinking about in terms of just not looking it up and maybe just writing it down somewhere, is 0.5. So this is when you have a sharp-walled entrance. We expect, of course, some kind of recirculation here, and you do get flow resistance to that. You can improve that K if you don't use a sharp-walled entrance. If you go to a smooth type of entrance, you can reduce that K considerably. Unlike this, it doesn't really matter whether it's smooth or sharp. You get the same K value. For this one, you get a different K value if you shape that inlet to be more conducive, essentially, to reducing any kind of recirculation. For the next set, I'm just going to put this on the screen. Hopefully you'll be able to see it here. These are some others, just examples of the kinds of things you'll find when you look on these tables. As I say, there are many of these tables. They exist in fluid mechanics books. They exist online. They exist in engineering handbooks. So here are some examples of things. So this is all, remember, for turbulent flow. We haven't dealt with laminar at all. Laminar K values are very different. These are pipe elbows, so these are places where the pipe is turning, in this case 45 degrees or 90 degrees. You can see that it depends on the diameter of the pipe. These are in inches, just because the table I had access to happened to be in inches. This one is 0.32. It is not important, obviously, that you look at do you memorize any of these. You will look them up as you need them. But you can see as the diameter of the pipe goes up, we see that in general, the K values seem to decrease. Small pipes seem to have larger K values if you make turns or things. But at any rate, these are the kinds of things you would just look up. 90-degree turn has more loss coefficient than a 45-degree turn. That's no surprise. But it's not just double. As you can see, it's very different from that. So you can't just assume that it's going to, the 90 degree is going to be just two 45s connected together. That's not how it works. For valves, there are many types of valves that these pipe networks have. These are just two pretty common valves. A gate valve is just a valve that literally this just goes up and down, and so it blocks off the pipe when it's closed, and it raises up to almost flush when it's open. So that's a pretty good valve. This is the fully open K value. So the fully open K values you can see are pretty low, particularly if you have a large pipe for these gate valves. This is what's called a globe valve. So this valve, as you can see, much more complicated. This little plunger would come down and close the valve, and when it's open, the flow still has to go through this contorted path. So there's clearly going to be flow resistance there. And look at these giant K values. These globe valves, even when fully open, have extremely large losses. So that's a different kind of valve here. Here's a T. Obviously, that's a very common thing. In that case, you have different resistances depending on when you're talking about the resistance when it goes in a straight line through the T, or then it goes upward, through the branch here. So if you go in the line, you see the K values 0.9, 0.9, 0.1, depending on the pipe diameter still. But they're much bigger if you're going to go to the branch flow, so 1.8, 1.4, 0.58. So we see the difference between which, the flow resistance, not surprisingly, greater if you're making this hard turn upward here. In general, The valves, of course, you can increase the K value a lot if you close the valves. The valves can go also basically to, to blocking the flow completely. That's their whole purpose. And they can slow the flow down. And the way they slow the flow down is they increase the losses. So this K is, varied a lot based on how open the valve is. Again, there are just charts that list, how much, or graphs that list, how K changes for different valve types as they get opened and closed. And in general, pipes that bend more sharply have higher K values than pipes that don't bend as sharply. So if you have turns that or have larger radii of curvature, or they don't bend as far, that's going to generally cause less loss than a sharp turn would, as you might expect. So anyway, again, you're just going to look these babies up if you need them. Because there are lots and lots of them and they depend on lots of different parameters, but they're not very hard to use once you've looked them up. You just plug them into that formula from last lecture and you can get what you need for pressure calculations and velocity calculations.